Previously, I calculated a second degree polynomial using Newton's formulation, and I demonstrated in Microsoft Excel with the help of these three data points. And we developed the interpolation values for uh, these x values, which are between 2 and they runs up to 6.9, and I plotted that one in the Microsoft Excel sheet. And now, if we would like to extend this one to a third degree polynomial, so we have to add a point. For example, I add here a point 11, and like the earlier data points, it is the ordinate value is the log of the value, log of x value. And then we can compute the third degree polynomial, so which is simply to add another term to it, and which is yes, here b3, and there will be the addition of another multiplier, x minus x2. And the beauty of Newton's polynomial is that the earlier calculations can be used to extract the new one. However, we have to compute the divided differences for at a next level. So we will require the calculation of third order divided differences. So for that very purpose, this is the location where we will come up with the constant b3. So we have to extend this calculation likewise. So it is the zeroth order divided difference at x3. So we have to compute the first order calculation. These are the slope values. Then similarly, the second order divided differences. These are computed as the slope of the first order slopes. And then this value is to be calculated as the third order divided difference. It will be this value, the divided difference at the at this level, at the fourth point, minus the divided difference at the third point, and divided by the abscissa values with the difference of 3 steps, because it is a third order divided difference calculation. So we have got the B3 constant. So we can calculate here a third degree Newton's polynomial and approximations at the interior points from this polynomial. So P3 of x, the previous approximation was P2 of x, P2 of x, the second degree polynomial. So at this calculation, I can make use of the earlier calculation, P2 of x. So this part is constant plus the coefficient B3. So I can pick that one from I$9. So this is B3 times x value at which the interpolated value is required. So x minus x naught. So x naught is at B 6, then x minus x1. So I can pick that one from its respective cell, B7 times x, which is at M6, minus x2. x2 is at B8. Yes. So the value has rightfully been calculated. Yes, here is the value. And then for all the remaining points, we can compute and we can plot. So this is the approximation as it has been plotted. So we can see that a light blue colored line has been created on it. To make it a bit different, uh, let's calculate the second order extrapolated values from here. So I repeat the calculation from for the points 7.2 and up to a point which is slightly less than 11, so 10.2. So we have this one, and we have got the extension of the polynomial which was computed from x0, x1, and x2, and the third degree polynomial, it is going to pass through the fourth point as well. So the pattern to the first 3 points, it is similar from the both polynomials. However, for fourth point, since it was not included in calculation for the second degree polynomial, therefore we have that discrepancy. So Newton polynomials are very handy for use because they make use of earlier polynomial calculations for calculating the next high degree polynomial.